So now that you've had a chance to see how Java threads are designed and a little bit of documented and are being evolved and improved in Java, let's talk a bit about another dimension of how concurrent programs are developed in Java. And this will have to do with so-called interaction mechanisms. And we'll talk about shared objects, which are also known as synchronizers, and message passing. So Java threads, of course, a Java thread, you can create a Java thread. It can go off and do its thing by itself. But that's probably the exception. Usually threads interact. Not all, but a lot of times threads interact. And when they interact, they typically interact with shared objects and/or message passing, or both. So we'll start by talking about shared objects. So shared objects are mechanisms that Java provides largely in the form of class libraries, although there are a few things built into Java, into the Java core execution environment, the virtual machine, and so on. And they're used to synchronize concurrent operations, running in multiple threads, of course, to ensure certain properties. So you can learn more about synchronization here. And one of the key concepts in synchronization is this idea of a so-called critical section. And a critical section is a section where, if all goes well, there's only one thread at a time that's doing its thing and accessing shared, often mutable state. So shared objects are usually used to synchronize programs to ensure things. And one of the things they ensure is that there's only one thread at a time running in a critical section. And we'll talk about why that's important in a second. So here's kind of the visualization of this. So we've got a bunch of threads, and they're taking turns doing stuff that are modifying and/or accessing the state of some kind of shared object. So here are some things, here are some properties we might want to ensure. One is atomicity. And atomicity is designed to ensure either an action happens completely or it doesn't happen at all. So it's kind of all or nothing. Anybody here remember Star Trek? If you're ever a Star Trek fan, a Trekkie, then there was the concept of a transporter beam. And you wanted to make sure that you were beamed atomically. It would be no good to beam, half of you and leave half behind, although I think that did turn out from time to time to be a plot device in Star Trek. If you're not a Star Trek fan, but you're a Harry Potter fan, then the concept of apparating or disapparating, I never quite understood the difference between disapparate and apparate, but whatever it is, you're kind of moving yourself from one place to another. And you don't want to leave part of yourself behind. Does anybody remember what that's called in Harry Potter, if you leave part of yourself behind? Splinching. So there you go. So that's atomicity. Another important property is mutual exclusion, which means that interactions between threads don't corrupt shared mutable state. This is what's often called mutual exclusion. It's a variant of what synchronization is. This is a couple of whimsical metaphors to think about when you think about mutual exclusion. These two vehicles ended up sharing the same space. And that's not a good thing. They were corrupted, right? They were in the space. And so you don't want that. You don't want to have you don't want to end up sharing things and having corruption and collision. So mutual exclusion mechanisms keep things apart. Another good metaphor for mutual exclusion mechanism is the protocol for using a restroom in an airplane, where you're supposed to wait while the restroom is occupied, and then when it's available or whatever, open, then you can go in, and when you go in, you shut the door and it locks it. So that's another kind of metaphor to think about mutual exclusion. Yet another property is coordination, which is designed to ensure that operations occur in the right order, at the right time, and under the right conditions. And the word condition is very important. We'll talk a little tiny bit about that here and there, although this is really a topic that's reserved more for a course that focuses entirely on concurrency and synchronization. And I like to think about, sort of passing a baton in a track and field event, in a relay race, as coordinating. If you don't get the baton handed off, then you don't do a good job and you lose and stuff, or get disqualified. And then the last set of properties that are really relevant in the context of shared objects and synchronization and so on is entry and exit barriers, which are used to enable a group of threads to wait for each other to reach a common execution point before they can proceed. So a classic example of an entry barrier would be the gates in a horse race. Or you can think about the starting blocks in a 100-yard or 100-meter dash or something like that, right? You don't want people to just start randomly, because that would perturb the results and make them meaningless. So those are some key properties that shared objects are intended to provide. And again, we could literally spend an entire semester talking about all this stuff. It's really fascinating. You can see a few examples of these. We'll touch on some of these just a teeny weeny bit in this course. Atomic operations and volatile type qualifier are examples of some things to get atomic operations. Synchronized statements and methods, reentrant locks, reader's writer locks. These are things that provide mutual exclusion. Semaphores and condition objects can be used for coordination. And of course, barrier synchronizers like cyclic barriers and so on can be used to provide barrier, entry and exit barriers. And you can read a lot more about these things here at this link. I also have lots of material in case you're ever curious. If you're getting ready to do a job interview and you need to know these concepts, I have a whole playlist here for my other class, and you can watch that if you're interested in learning more about the synchronizers in Java. Like I said, we are not going to talk a lot about them in this class, and you'll see why when we start talking about parallel programming. And one of the things, without giving away too much of the suspense, one of the things that parallel programs do is they partition the data up in such a way that there is no need to synchronize often because you're having different threads working on different parts of the data in parallel, and never the twain shall meet. So we'll talk a bit more about that as we get further along. The other form of interaction in a concurrent model is message passing, where you have one or more producer threads sending messages to one or more consumer threads, typically using some kind of blocking queue. So you have one or more threads sending data to other threads, and they put the data into a blocking queue. And all a blocking queue means is that if the queue is full, then threads that are trying to produce the data have to block, wait till there's some room in the queue. And likewise, if you're a consumer thread and there's nothing in the queue, then you have to block or wait until there's room. The basic idea behind message passing is to decouple producers and consumers so they don't have to access shared objects directly, which leads to some simplifications of certain things. You're kind of breaking the chain of connectivity. And there's a whole slew of Java thread-safe queues that are used for message passing. There's array and linked blocking queues. And these are all done basically in FIFO order, first in, first out. There's priority blocking queues where things are inserted in any order, but they're removed by the order of their priority. There's a really wacky thing called a synchronous queue, which is used for certain Java thread pool models. And there's also something called a concurrent linked queue, which is really not so much a blocking queue as just a queue that you can put things in and out of for multiple threads without having to worry about corrupting the state of the queue. OK, so that's the end of the quick overview of how concurrent programs are developed in Java with respect to thread interactions.